Well, good day, everybody, and welcome back to Chem. And we are in our discussion of equilibrium. So let us take a look at this. Consider nitrogen gas plus three hydrogen gases in equilibrium with two ammonia gases. The delta H equals a negative 92 kilojoules, and we're going to assume this is at equilibrium. Okay, and we know something about equilibrium, and now the question is, in which direction will the equilibrium shift if moles of hydrogen gas are added? Okay, I don't recall us talking about this kind of stuff last time. Do you? No, I think we need some more notes. So let us come over here. Let's do a quick review. We're talking about equilibrium, right? And we said over here equilibrium was a steady state in a reversible reaction in which the concentration of the reactants is constant and the concentration of the products is constant. Now, those are two different constants, but they are constant. Or another way to say this is that this is a steady state in a reversible reaction in which, and I like this one, I guess, a little better, but we don't quite understand it yet, in which the rate of the forward reaction equals the rate of the reverse reaction, right? So if we go back to our question here, for this to be at equilibrium, we have to have a reversible reaction. That means my nitrogen and hydrogens react to form ammonia, but at the same time, my ammonia decomposes to form hydrogen and nitrogen. And if these rates are equal, if the forward rate equals the reverse rate, then I have an equilibrium. Good. So that's kind of the definition. And we said that we had something called an equilibrium constant, right? And we call that a KEQ. Some people call it a KC, but an equilibrium constant. And that, for all equilibriums, we have this constant, and that constant is equal to the concentration of the products raised to a power, and this power is based upon the coefficients, right, over the concentration of the reactants raised to a coefficient, we'll call it M, raised to a power, and that's based on the coefficients in balanced equation, right? And when we're putting this together, this only applies for things that are aqueous and gases. It does not apply for liquids or solids. Yoink, we don't put those into our KEQ. Now later, you'll learn that there's also something called a KP, but for us, KEQ is fine. And so if I were to write my KEQ here, okay, so let's clean this up a bit. I'm confused even looking at that mess. So if we wanted to write a KEQ, we'd say, okay, I need to find my products. Here are my products. That's equal. So I want to take the concentration of ammonia, and I'm going to raise it to a power. I'm going to raise it to the coefficient there. Divide it by, now notice these are both gases. These are gases or aqueous, so we're cool. Divided by the concentration of N2 times the concentration of H2 to the third. So that's my KEQ. Good. So there we go. That's a review of KEQ. And we said, hey, if my KEQ is much, much bigger than 1, that means products are favored. That means I have more products at equilibrium than reactants. Products are favored. If KEQ is much, much less than 1, that means, hey, I have a big denominator. That means reactants are favored or predominate. Predominate. Yahoo! Meaning there are a lot more reactants than products at equilibrium. Good. Now we want to move on, and I'm going to use a blue pen for this. Yips! And we want to talk about some French dude. We want to talk about, I think he's French, Le Chatelier's principle. And we're not talking about the head of his school here. Prince, not principal, principal. Yeah, Le Chatelier's principle. Good. And what's Le Chatelier's principle? Here we go. What it stated, it says that when a stress is applied to a system at equilibrium. Okay, so that means I have a reversible reaction and I have my forward rate equal my reverse rate, and I'm going to put a stress on that. Now I'll explain further what these stresses are, or at least the biggest ones. When a stress is applied to a system at equilibrium, the equilibrium will what? Shift. What does shift mean? It means it changes for a time being. The equilibrium will shift to reduce the stress. Got it? Okay, when a stress is applied to a system at equilibrium, the equilibrium will shift to reduce the stress. Okay, so that's Le Chatelier's principle. Good. And I think we can better understand that when we start doing some examples. Let's take a look at stresses and shifts. Okay, good. So let's go back to our question, and we have several of these stresses laid out here. Number one, what happens if let's clean this up. What happens if I add moles of hydrogen gas? So that means I'm going to change this. All right. So I have a system at equilibrium, and I'm going to change my reactant, and I'm going to add more moles of hydrogen. What does that really do? Well, really what I'm doing here, let me take this way over here. What am I really doing here is I am changing concentration. If you change the concentration of reactant or product, then that is a stress. Okay, so this is one stress, changing concentration of reactant or product. Now, how does this affect things? Okay, let's take these one at a time. Let's talk about reactants. Reactants. Okay, good. And I can do two things with the reactants. I can increase concentration or decrease concentration. So first, let's take number one, and we will increase the concentration of a reactant. Okay, and so let's come back here. Well, I'll tell you what, we need something. Let's go up here. There we go. Something clean. So let's say I increase the concentration of my silver ion. What's going to happen? Well, my equilibrium is going to want to shift. Now, what that means is when I increase my concentration of silver, the equilibrium will want to decrease that concentration, okay? The stress is increasing the concentration, so the equilibrium wants to do the opposite. So it wants to decrease the concentration. Well, how are you going to decrease the concentration of silver? Well, what's going to happen for a short time is my forward rate is going to be higher than or bigger than my reverse rate. And so what will that mean? That means over time, let me go with a green pen, over time, this concentration starts to drop, this concentration starts to drop, and this concentration starts to increase. Once we get to a certain point, then these two guys level out again, and we have a new equilibrium established. And we would say that the equilibrium shifted, for the time being, shifted toward the products. Okay? So when my silver goes up, the equilibrium will want to reduce silver, and that will mean that it will shift toward products. Okay? Good. And you understand what shift means. It means for time being, the arrow towards the reaction rate toward the products is greater than the reaction rate towards the reactants. Got it. Okay, so let's clarify that. Let's codify that here. Good. What's going to happen? Equilibrium shifts to reduce that concentration, meaning equilibrium shifts toward products. Got it? Good. Now, what's going to be the opposite thing that can happen here with the reactants? I can reduce the concentration of a reactant. And so if we go back here to our beautiful picture, I think I should sell those, don't you? Let's say we reduce the concentration of silver. That means the equilibrium is going to want to do what? The equilibrium will shift to increase silver concentration. Boy, that's a nice arrow, isn't it? Increase silver concentration, meaning it's going to shift toward the reactants, and the reverse reaction rate will be greater for a while than the forward. And eventually, when we get this increased enough to remove the shift, the stress, these arrows will equal out again. So that means the equilibrium shifts to increase the silver concentration. How is that? That means it has to shift towards the reactants. Got it? Okay, here we go. Zoink. Okay, so this is going to do what? Equilibrium shifts to increase. And let me clarify this here. Increase my concentration of the reactant. And so that means what? My equilibrium shifts to the reactants. Okay? Good. And these are the ones they tend to want you to know is shifts towards the products or shift towards the reactants. Good. Now we can ask the same questions about the products, right? And really then it's just the opposite, right? Number one, what happens if I increase the stress? What happens if I increase my product concentration? What's going to happen? Well, my equilibrium is going to shift to decrease product concentration. That means what? Does it shift towards the products or towards the reactants? Well, it shifts away from the products, meaning my equilibrium will shift to reactants. It means it'll shift to make more reactants. And if it makes more reactants, it is consuming products. All right. And then come back here. 2. Then what happens if the stress is a decrease in product concentration? Okay, so then what's going to happen? My equilibrium will shift to increase product concentration. And how is it going to do that? It means my equilibrium will shift toward, we say, the products. It means it'll shift to make more products and consume more reactants until we establish a new equilibrium. Cool. There we go. That's all we need to know. So let's take a look at our question. In which direction will the equilibrium shift if moles of hydrogen gas are added? So I add moles of hydrogen gas. What's that going to do to my concentration? So that means the stress is an increase in the concentration of H2, right? Well, then what's my equilibrium going to do? My equilibrium shifts to do what? To decrease hydrogen concentration. How do I decrease hydrogen? It means I have to use it up, meaning I have to make more ammonia. So that means my equilibrium shifts toward the products. Woohoo! Hey, that's a piece of cake. Once you understand that this stuff is really easy. Okay, now let's take a look at the next part. If moles of H3, if moles of ammonia are added, okay, let's clean up my mess up here. Magic. Woohoo! I wish I could take care of my life that way, don't you? Anytime you had a problem, you just circled it with an eraser and hit it, and all the problem goes away. That would be nice, although I probably wouldn't learn anything, right? Okay, so if moles of ammonia are added, so I add moles of ammonia, what's going to happen to my ammonia concentration? My ammonia concentration is going to increase. That means what? Okay, so my ammonia concentration increases. That's the stress. What's the equilibrium going to do? Well, the equilibrium, yikes, let's try to spell. The equilibrium is going to do what? The equilibrium is going to reduce the ammonia concentration. And how can it reduce the ammonia concentration? It is going to shift. The equilibrium will shift toward my reactants. Cool. All right. Here we go. What if the moles of ammonia, not ammonia, that looks to me like nitrogen. What if the moles of nitrogen are reduced? Okay, so I'm going to reduce my nitrogen. So that means my concentration of nitrogen decreases. So and that's going to be my stress. So what is the equilibrium going to do? Well, the equilibrium wants to increase concentration of nitrogen. And how can that happen? Well, it must make more nitrogen, meaning the equilibrium will shift toward reactants. Yahoo! Okay, moving on. If the volume of the reaction vessel is decreased, so who cares about that? What's that have to do with? Well, this has to do with really what happens. I'm dealing with gases here. What happens if the volume of my vessel is decreased? Well, that affects what? Pressure. Okay, that is another stress. So let us go down here. Another stress, let's go with another color. Another stress is, yeah, take it right off here. Zinc. Changing partial pressure of gas reactants or products. Okay, now we have to be a little careful here. We're talking about partial pressure, and that means this is not all pressures. First of all, this means that this is a pressure change caused by change in volume. Now, I could also change my partial pressure by adding more of the product or reactant, but that's already being covered over here in changing concentration. So we're going to just focus on if I have a pressure change caused by the change in volume, okay, that applies here. Good. Number two, this only applies to gases. Doesn't affect liquids or solids. So we only look at the gases that are in our reaction when we try to solve this. Okay, now here's the way. I'm going to need more space, so let's come down here. I am going to have to need a big explanation. Zinc. So how do these things change? Okay, I can first increase my pressure by decreasing volume, right? What do I do? Okay, so stress is the increase in pressure. So stress is the increase in pressure. So what's my equilibrium want to do? My equilibrium wants to do what? The equilibrium wants to decrease pressure. And how is it going to do that? Well, pressure is caused by what? Moles of gas. So that means my equilibrium will try to create fewer moles of gas. And so what does that, how will it shift? Well, that means it's going to, my equilibrium will shift toward side with fewer moles of gas. And how do I figure out the moles of gas? I look at the coefficients. So if I have, let's say I have something like, well, let's say I have something like this. How many moles of gas do I have in this equation? Well, I have 3 here and 1 here and 2 here. That means on my reactant side I have 4 moles of gas, and on my product side I have 2 moles of gas. Okay, so that's how I make the comparison. And so our statement over here is if my pressure is increased by a reduction, how do I increase pressure? Well, I have to reduce volume. So if my pressure is increased, oh, I already said that over here, right? If my pressure is increased by reduced volume, my equilibrium will shift toward the side with fewer moles of gas. And in this case, fewer moles of gas is which side? Right here. Wow, magic. And so it would shift toward the products in this case. Okay, what happens if we have the opposite effect? What happens if I woo, magic, yellow. How did I get yellow? What happens if I decrease my pressure by increasing volume? Okay, so that's my stress. So the stress is a decrease in pressure. So that means my equilibrium is going to want to do what? The equilibrium wants to increase pressure. How is it going to do that? By increasing moles of gas, right? And so it will shift toward side with more moles of gas. Got it. Perfect. Wunderbar. Ach du Liebe. Why did I say ach du Liebe? That doesn't make any sense. That's okay. I often don't make any sense. Here we go. So my volume of the reaction vessel is decreased. So volume is decreased. What does that mean? Volume is decreased. That means pressure increases. So what's my equilibrium want to do? This is my stress, right? So my equilibrium wants to remove that stress. And so what does it want? It wants pressure to decrease. How do we decrease pressure? Well, we have to decrease moles of gas. And which side has more moles and which side has fewer moles? I have 4 moles of gas here, 2 moles of gas here. So what? If every time I go in this direction, I go from 4 to 2. Every time I go in this direction, I go from 2 to 4. Which direction gives me fewer moles? This direction. So that means my equilibrium will shift toward my products in this case. So the equilibrium shifts toward products. Got it? Perfect. Okay, if heat is added, causing an increase in temp. Heat. Okay, heat is added. All right, the next thing. Where are my Chateliers? The last effect we want to talk about, and we're going to have to come way down here. Way. Na 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 na. Na 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 na. I just need a wider board, don't I? Na 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 na. I like how I can go infinitely up and down, but kind of restricted going left to right. Good. Adding heat. Heat. Changes in heat. Changes in heat, which means really changes in what reflects a change in heat? Changes in temperature. That's what we have to understand is whenever we have a change in temperature, it's really meaning heat is added or taken away, right? Temperature change means a change in average kinetic energy, but how do those kinetic energy changes occur? By adding or taking away heat. So we want to talk about a couple situations. And the first thing we have to talk about here are we have 2 types of reactions. We have exothermic and we have endothermic. Endothermic. Now, what does it mean, exothermic? Exothermic means heat in this reaction is released. That means heat is essentially treated as heat is a product. It is created in the reaction. Got it? So with an exothermic reaction, heat is a product. Now, how do we know something is exothermic? They say it's exothermic, or the delta H is less than 0. So when we see a delta H equaling a negative number, it's exothermic. For us, that means heat is a product. And so you would have A plus B going to C, and you'd write down, at least in your head, plus heat. Got it? What if it's endothermic? Well, that means heat is used up. That means heat is consumed. And what else is consumed in a reaction? Well, the reactant. So that means heat is a reactant. Good. And how do we recognize that? Delta H is greater than 0. And so we'd have to think of it as heat plus A plus B yields C. Now, once we have this set up, we treat it just like a change in concentration. So, for an exothermic reaction, what happens if my stress is an increase in temp? Well, if it's an increase in temp, what must have happened? We must have added heat. Okay, now where is heat? Heat is a product. So that means I've increased my heat. So what does equilibrium want to do? Equilibrium wants to do what? Decrease heat. How is it going to decrease heat? Well, heat is a product, so my equilibrium will shift toward reactants. Right? It wants to consume this, so that means the reaction has to go in that direction. We better make these two-way, right? Zoink, zoink. Good. And now what happens if my heat is decreased? Well, that means my equilibrium is going to want to do what? Equilibrium is going to want to increase heat. And that means equilibrium will shift toward products. Yahoo! Right, and what causes this change in, what causes that change? Decrease in temp. So if someone says, hey, what happens when the temp is decreased? Well, really that means what happens when heat is reduced? Well, for an exothermic reaction, my equilibrium will shift toward my products. What happens for an endothermic reaction? Well, just the opposite. Okay, so when I increase my temp for an endothermic reaction, what happens? That means heat increased. That means my equilibrium wants to do what? My equilibrium wants to decrease heat. How do I decrease heat if heat is a reactant? Well, my equilibrium will shift in what direction? Well, if heat's a reactant, it wants to shift in that direction. So equilibrium will shift toward products. Oh, got it. Hey, this is a piece of cake now. It sure is. What happens if my temp drops? Well, if my temp drops, that means what? That means my heat dropped. So that's my stress. So what is my equilibrium going to do? My equilibrium then wants to increase heat. So how do I increase heat? Well, heat is a reactant. That means my arrow has to go this way, meaning I need to convert C into A, B, and heat, meaning my equilibrium shifts toward reactants. Okay, there we go. Let's take a look at our question. If heat is added, well, first of all, what kind of reaction is this? Aha, my delta H is what? Negative. If delta H is negative, what did we say that is? That is exothermic. So I have an exothermic reaction. Let's clean this up a little bit. I have an exothermic reaction, so where's heat? Exothermic means heat is created. It is produced. So that means heat is a product. Okay. So if heat is added, so my temp goes up, which means heat goes up. So what does my equilibrium want to do? My equilibrium wants to reduce heat. How do I reduce heat? I go back up here. I want this to become smaller. How does it become smaller? By going this way or by going that way? Well, if I go from left to right, I'm creating heat. So no, if I'm going from right to left, I'm using heat. So I want to go that direction. So that means my equilibrium shifts toward reactants. I almost said products. That would have been wrong. Got it? Okay. Woo! You guys try this one, and then we'll call it a day. In which direction will the equilibrium shift if Cl2 is added? Where's Cl2? Here's Cl2. It's a product. So my equilibrium shifts toward what? Well, I want to, if I've added Cl2, so my equilibrium wants to reduce CO2. How's it going to reduce CO2? By going in that direction. So it shifts towards my reactants. Good. If moles of PCl5 are added, here's moles of PCl5. What am I going to do? The stress is an increase in that. So that means my equilibrium wants to decrease that. How do I decrease that? By shifting toward the reactants. I hope I'm not going too fast for you here. If moles of PCl5, oops, looks like we have a problem here. If moles the volume, okay. It looks like we should have really two questions here. So let's just get rid of this one. Zoink, zoink. If the volume of the reaction vessel, you know what? I know what that should be. If moles of PCl5 are, oh, hold it. I made a mistake here. Look at what I did. Let's go back and fix this. I made a big mistake. I couldn't read. If moles of PCl5 are added, there we go. We're talking about moles of PCl5. That means what? The concentration of PCl5 is increased. So what does my equilibrium want to do? My equilibrium wants to decrease moles of PCl5, right? So that means I want to bring this down. How am I going to bring that down? Well, it means my equilibrium wants to go in this direction, and so my equilibrium shifts toward products, right? Shifts towards products because by going towards products, I will consume this added PCl5. Okay, if moles of PCl3, I don't know what I was doing there, so let's just skip that. If the volume of the reaction vessel is decreased. Okay, so if my volume decreases, that means what? That means my pressure increases. So then what does my equilibrium want to do? My equilibrium wants to decrease pressure. How do I decrease pressure? I want to decrease moles. Moles of what? Moles of gas. Okay, how many moles of gas? Well, here's gas, here's gas, here's gas. I have 2 moles on this side, right? Because I have 1 here and 1 here. And I have 1 mole on this side. So I have 1 mole on my reactants and 2 moles on my products. I want to decrease moles of gas. So which way will my reaction shift? My equilibrium will shift towards the lower number of moles. So that means it will shift toward reactants. Reactants. And finally, here we go, the last one. If heat is added, okay, I'm going to add heat. So heat increases. What must I know? I must know whether this is exothermic or endothermic. I look at this. It's a positive number. That means it is endothermic. Endothermic means what? Heat is a reactant. So heat is over here. So heat plus PCl5 yields PCl3 plus Cl2. If I increase my heat, then what does my equilibrium want to do? My equilibrium wants to decrease heat. How do I decrease heat? How do I bring this down? I have to do what? I have to use some of it, meaning I want my reaction to go from left to right. So for a short period of time or for a period of time, my forward rate is greater than my reverse rate. And so that would mean what? My equilibrium shifts toward products. All right, I hope you understood this. I think this one probably went a little long. Oh my gosh, it went real long. Sorry, folks, but next time we're done with equilibrium. And I hope you have a good day.